case high-fidelity simulation of rotating parts focuses on conducting high-fidelity CFD simulations of a drone rotor with moderately complex geometry. Modelling turbulent flows at high Reynolds numbers is both challenging and costly, requiring large meshes to capture all flow features. Advanced mesh refinement and in-situ data analysis are employed to enhance the accuracy and efficiency of aerodynamic simulations. To achieve high accuracy, KTH researchers executed simulations using incompressible CFD solvers based on the spectral element method, known for fast convergence and low numerical diffusivity.
We employ adaptive mesh refinement to dynamically adjust the grid, applying high resolution to critical regions to minimize error and reduce simulation cost. However, adaptive mesh refinement alone is insufficient to reduce the massive data produced, so we use in-situ techniques like streaming algorithm for proper orthogonal decomposition and predict time averaging errors with uncertainty quantification.
Finally, the CFD solver is coupled with an acoustic solver to predict noise. Performing an accurate simulation at a reasonable cost is crucial for modern research.
We are currently performing pre-production runs of the Iowa drone rotor in Hoover configuration, testing various components of our workflow. By gradually increasing the number of refinement levels, we enhance resolution and verify whether the correct domain regions are refined and whether the refinement is localized. Simultaneously, we test in-situ workflow by visualizing vertical structure of the flow, demonstrating our ability to accurately model fine flow features in the relatively complex case.
Currently, the KTH team is using the CPU version of their adaptive mesh refinement solver, which limits the size of the cases they can simulate. The next step is to implement and utilize a GPU version of the code. Additionally, KTH researchers will focus on coupling the CFD solver with the acoustic solver to predict noise.